systems that can enact this kind of personalization. So why might we want to connect instruction in high school to students' interests? Are their interests even related in meaningful ways to high school mathematics? I think is an important question. I wanted to show you guys 2 quick videos of interviews. These are 8th grade students who have not yet taken Algebra 1. The first student is talking about Instagram and her activities when she's on Instagram.
Basically just like sharing like pictures of like whatever you're doing, so you can like have things to follow you and follow people to calculate, and if you put like hashtags, like sometimes you get like a bunch of likes. And there's like Instagram, and these people have like 25K followers. I did hashtags, so I get anywhere from 30 to 50 to 60.
When you don't do hashtags, how many people like your pictures usually?
Well, last time we didn't do a hashtag. Probably 25.
So how many hashtags would you put on any one picture?
Sometimes I put like 10 or less. But I follow like 200 something and I have 442 followers.
How long did it take you to get 142 followers?
I've been on Instagram since September.
So what about your friends? How many followers do they have?
Oh, my best friend who's in math lab with me, she has 1,100 something.
Wow, why does she have so many followers?
No, sometimes you can get a shout out from people to like people about to follow us, like you give her a shout out, go follow them, and you follow them.
So this is a student who does not have a strong interest in mathematics. She's been tracked into that lowest mathematics class at her school. You can see she knows like a lot of very specific numbers about her Instagram and how things change as different variables change, like how many hashtags she uses. So this is another student from the same class. He's a little quieter, so I'm going to see if I can turn up the volume. And he's talking about his interest in making Lego stop motion videos. So he takes Legos, he moves them small amounts, and makes a video that makes it look like they're moving.
Well, basically, I use like to watch videos and also make videos.
What kinds of videos do you make?
Oh, they're basically review videos, and I like to make stop motions. They're basically figures. Take a picture, move it slightly, take a picture, move it slightly, take a picture. So all of that, doing all that, it makes it look like it's moving. It's just a series of pictures.
What kind of software do you use or how do you do it?
If I had a free trial with Sony Vegas, but since I don't have that now, it costs I think $100, and I use Windows Movie Maker. So, or just for seconds, because let's say you just use one. If it will go slow if you put like 1 frame per second, that would be very slow. So it would have to be. Let's say these are 2 pictures. These pictures, 3 frames per second, so that'll be like 1, 2, 3. So that'll be how many frames it would show to go with real life, and that it would look like really just like a robot.
So how many frames per second makes it look
I
realistic?
use 6 or 7 frames per second.
And that's 6 or 7 different pictures you take in every second of the video. And how long are the videos that you do?
Well, some can be up to 3 minutes, some can be up to 5, but they take a long time to make. Like 2 hours goes into like 5 minutes of video.
Okay, so the point of these videos is that students have rich engagement with their interest areas. Once you start talking to them and start really trying to draw out from them how they're using numbers and seeing numbers, you get a lot of super interesting relationships that they're thinking about in their lives. There's a lot, I didn't show one with sports, but there's a track star who tracks how long it takes him to run different distances over the course of a school year as part of his engagement in track. And many, many students have this type of engagement with their interests. At the same time they have these rich engagement with their interests, they're not making sense of school-based mathematics, and their attitudes towards mathematics, specifically its usefulness, its relevance, show a huge drop right around 7th, 8th, 9th, 10th grade is where we see the biggest problem area. So what my research does, and I'll close this in just a second, is I explore opportunities that are offered by personalizing learning to students' interests. And I'll just briefly talk about a couple different ways that we have done personalized learning in the past. One is through technology systems like Cognitive Tutor Algebra. We create interventions where the intelligent tutoring system will give students different problems based on their interest categories. We're also doing this with Reasoning Mind, which is used in Dallas. There's a new curriculum, Mathia, where students give stars about how interested they are in different topics, and Mathia will give them problems based on those interests. And the results for this type of personalization have been quite good, both in Cognitive Tutor, this one was in Reasoning Minds. We had great results in both. We're also, skip past this one, looking at kind of classroom interventions without technology where we can personalize learning. So what we're doing now is we're working with middle and high school students, and we're building interventions where students during class write and solve problems based on their interests. So here we're getting the students to think about their experiences. We're going to have them go home and go into their communities and think about how algebra is used there. Come with their experiences to the classroom, use them to pose problems that relate algebra to their interests, to share problems. See two of these written down here. This one is about Clash of Clans, which uses a lot of algebraic relationships, actually. A lot of these games do. This one is about a student playing Ultimate Frisbee and how he thinks about the progress that his team needs to make. And we found that even students who have little or no exposure to algebra, even the students who are at the very bottom when they're entering algebra, they're able to write and solve algebra problems if they're about their interests. And this not only improves their ability to write these abstract equations, it also improves their interest in learning algebra. So what we found in our studies is normally the interest in mathematics declines over adolescence, and we can essentially get it to be flat by using personalization interventions, which is something, that's progress. So we've conducted a lot of personalization interventions at this point. I just wanted to summarize what we've learned, because there's definitely ways to do real-world connections well and ways to do them poorly. And we've kind of come up with 4 principles that if you honor these principles, and the research says you'll see good results for this approach. If you don't honor them, the positive effects kind of generally decrease. The first is that when you're making real-world connections, they should be deep and meaningful and connect to the ways in which your students actually use quantitative reasoning when they're pursuing their interests, or the way in which professionals actually use quantitative reasoning in the real world. They shouldn't be these kind of artificial problems. The effects that you can get from personalizing these artificial problems or giving them to students are not very large. The more meaningful the problem becomes, the better students learn from it. The second is that this approach seems to be better if the grain size is relatively small, meaning if you know your students well. You know the kinds of things that they're interested in, you know the kinds of numbers they're seeing outside of school, you know their culture, their community life, and how you can bring that into the classroom. The third one, we've just found in some recent studies, is that ownership is really important. You don't want to, come up with this kind of scenario and impose it on your students. You want to give students ownership of how mathematics is being connected to their interests. So engage them in the conversation of what they're interested in and how it relates to mathematics. So when we're having them write their own problems, that's a really high ownership activity because they're taking their own experiences and then you're helping them to make it mathematical. So they have a lot of ownership of it. And then finally, our last one is richness. So, all of these rich, situated, meaningful problems, sometimes when students are solving them, the mathematics can kind of get lost. The TEKS can kind of get lost in all of the richness and all of the interestingness and fun. So what we always try to do with our interventions is to balance this rich problem solving with the teacher making very explicit connections to the TEKS and making sure that everybody understands what those abstract principles are afterwards, not just letting it kind of hang out there and figure that students are kind of gleaning the things they need from these problems. The teacher needs to come in at the end of the problem solving and explicitly make sure that these concepts are being brought out. So, some suggestions for how to start to implement real-world connections in your classrooms. One is just to get to know your students' interests by talking to them. It sounds really obvious, but I was a teacher, and I didn't really have these deep conversations with students about the quantitative reasoning they do until I became a researcher. And it's not difficult to do. Most of the conversations I have with kids are just 5 to 10 minutes long, and they provide me with such rich insight. Another thing is, a lot of teachers just feel like they don't really know the real-life connections well enough to be able to pose these really excellent problems. And there's a lot of resources for how you can kind of educate yourself about what these connections are. One thing that I like doing is visiting sites that kind of bring mathematics into the real world and show me how the connections are made. So all of these are great places you can go to get ideas for real-world connections for your secondary math concepts. We have a Museum of Geometric Art in Dallas. We have, of course, the Pro Museum. The Rory Myers Children's Adventure Garden, even though it says children's, it has high school geometry level concepts and how they occur in nature in these exhibits. There's also a variety of workshops, including the ones that we offer here at SMU, like the crime scene investigation workshop, as well as the ones offered by the Pro Museum. They have a booth out. We also have our MMT and Master Mathematics Teacher and Master STEM Teacher programs at SMU, which have a big emphasis on this. And finally, we have some excellent lesson resources, which we are going to pass out, which give you really high-quality places you can go to get secondary mathematics problem scenarios that connect to the real world in authentic ways. And I really only put a link on here if I was very, very confident in the material on the website, if I had used it heavily in teaching before and I felt like it was a high-quality connection being made to a real-world situation. Finally, choosing your textbooks carefully. There aren't very many good secondary ones out there, but if I had to recommend some, I would say Core Class, University of Chicago School Mathematics Project, Cognitive Tutor, or College Preparatory Mathematics are the ones that our studies have shown are the best. All right, and we'll have just a couple minutes for question, it looks like, but before we moved on to there, I just wanted to mention our Master Mathematics Teacher program here at SMU. You take 4 courses in K-12 mathematics teaching and receive a Master Mathematics Teacher certificate. These courses also count towards a master's degree in education, or they can be taken as a standalone for the certificate. For more information, you can email me or visit our website, which discusses this opportunity. Also, brand new this year, the contact information is the same, is our Master STEM Teacher program. In this program, you take 4 courses that focus on STEM integration. So if you're really interested in connecting mathematics with science or engineering or technology, but you don't feel like you have the knowledge base to actually make it happen, these courses are really ideal for that situation. And again, you can contact me if you want more information. They can be taken standalone as a 4-course sequence, or they can be part of a master's degree. And our application deadline is March 15th, so it's coming up really quick. All right. So we can open it up for discussion for the last question, 6 minutes.
So,
Can you put that back on?
Sure. So what questions questions do you guys have about meeting the process standard of embedding mathematics in real-life situations?
Main question we have is algebra 2, or you're starting, okay, 6th grade they start to lose it, 5, 10th they're gone, and we get them in the day. So, like, will these activities like resuscitate them, or should we just do this to practice, and then hopefully the 6th grade teachers will eventually incorporate this and we'll have this glorious future of this mathematical rainbow, right? Like, I'm wondering what we can apply tomorrow, or I guess we're going to go to school tomorrow, Monday. Right?
Well, I think it is a little trickier in Algebra 2 because if they weren't taught using these methods in Algebra 1, it's hard to suddenly spring it on them. So you might need to start with some more basic activities that maybe encompass Algebra 1 content if they don't have that foundation. Because if they just got through Algebra 1 and didn't actually understand any of it, then the foundation that they need to problem solve in Algebra 2 is not going to be there. But there's no point in just getting them through Algebra 2 and having them not understand it. The foundation needs to kind of be built one way or another. And that's part of the reason we have 2 years of algebra, and the reason why it's so tragic that Algebra 2 is no longer required. Because you really need those 2 spiraling years to delve deeper and deeper into the content, even the Algebra 1 content and the way it comes up in Algebra 2. So I would say we should build a foundation, but it's definitely doable. Other questions?
So what would you say elementary campuses could do to support them?
So elementary campuses, I think there are just so many great programs in elementary mathematics that give this concrete to abstract progression. So a really famous one is cognitively guided instruction, or Number Talks is another really awesome program. There's also great curricula like Mathematics in Context, Everyday Mathematics for elementary. You guys really have a lot more of the resources, I feel like, than the secondary people get. And the research in elementary is very similar, that starting with concrete, and then when we say abstract in elementary, we mean like numbers and addition symbols. Instead of, the traditional X, Ys, but the principles are all the same.
Hi, I'm Cornell Lacey. I'm a high school math teacher at the Rock Obama Leadership Academy. I'm a third-year teacher, and this is just a general question. So you mentioned the importance of having to have both year 1 algebra and year 2. So I teach all the high school courses, and I just was dying to ask, why do we have the geometry in between the algebra 1 and 2 years? Or does anybody teach it? Because I remember HISD maybe a year ago or so was contemplating switching the algebra 2 to occur right after algebra 1. But does anybody know why that is, or if that's actually more, if that's just for them to choose their perception of algebra?
Yeah, it's interesting. One of the curriculum I recommended, Core Plus, doesn't go with the Algebra 1 geometry, Algebra 2 progression. It actually integrates across the 4 high school years. And they've done a number of studies on what the results of that integration is, and they've all been very positive. So I think it's just, at this point, like tradition that keeps us kind of locked in this sequence, Algebra 1, geometry, Algebra 2, rather than what the research actually suggests is going to be best. But now that we're throwing out Algebra 2, for some students at least.
But you know what, I guess I can answer that. If you look at geometry, a lot of questions are used with the equations nowadays, because they have to find out the angles, measurement, and so they use one-step equation, they use two-step equation in geometry. So it's kind of like continuation, except the symbol that you put, like degrees or the new symbol. But kids need to relate that, and it goes from one to another.
Right, so we maybe wouldn't want geometry before Algebra 1, but we might want them, like this curriculum has them integrated across.
So if you look at the curriculum, it's more like an algebraic concept.
It's seriously, that's all you're doing, you're practicing what you learned in Algebra 1 in geometry.
But except that
you
you
use those geometric terms like proofs,
measuring
that
those
sort
or
of.
anything
But
like
you
that.
still come back to my equation to solve this is, type thing. That's my interpretation of it, but I'm going back to what Dr. Walken said.
And let me tell you one thing, if you look at the algebra concept in exponential functions, they ask students on the EOC exam, find out the volume of a sphere, but they have to use the exponential functions on that. by using the formula of law of exponents. But actually, that's going back to geometry, where the kids are finding the volume in the surface area of the prism or anything like that. So it is a continuation of algebra.
Other questions?
I am an elementary teacher, and we are starting seeing in fourth grade some like algebra concepts, like using letters to represent mathematical problems. But is there any research behind or any reason to start with some basic concepts in elementary? And just a comment, they start with the concrete, with the abstract first, and then they move to the concrete after that.
Interesting.
So they do it the opposite way. We're utilizing Pearson, and at least for that concept, they start with concrete and equations, and then they move to the work problems and real-life applications.
Yeah, that's really, especially in fourth grade, that's a really interesting approach. I think that there has been a big push to get the algebra earlier in the school sequence, and the research on it actually is quite good. But the research that has shown good models for it are the ones that are using these everyday experiences to introduce children to the ideas behind algebra, and then gradually having them generate how to symbolically represent them, if they symbolically represent them at all. And the idea there is also that you're very open-ended in what counts as a symbol. Like, it could be a phrase. It doesn't have to be like an isolated letter. They just have to understand the idea, and they can eventually transition as they go through middle school to using the individual letters. So I think understanding that the progression of different students is going to be different with using the abstractions and not imposing it on all of them is kind of what the research says, along with introducing it using the real world concrete situations.
I'm just curious, have you done any research on the implementation of using graphing calculators earlier and earlier in their education, and if it's hindering students' abilities to actually do the math, or if it's helping them, or if it's not changing anything?
So I don't have a very detailed, fine-grained knowledge of this research, but generally the math education community supports early use of graphing calculators, I would say, as very important tools that students can use. Now, the types of tasks that we forward with graphing calculators are all often like very generative activities where they're experimenting, changing different parameters of a function and seeing what happens. So it's not like plug in this function and find this point. They're kind of inquiry, discovery type activities that take advantage of the efficiency of the graphing calculator to create a lot of graphs quickly, or to expedite the solving of expressions they already know how to solve, or something like that. So I don't think it's harmful to do it early if you're using good pedagogy with them.
So I try to stress to my students whenever we're learning different equations to get married to the concept, don't get married to the variables. And what's your take on, but then that's kind of difficult when you see stuff like volume equations or something like that. But I saw a lot of students that were getting caught up on y equals mx plus b, m has to be the slope, b has to be the y-intercept, versus understanding the coefficient that is being multiplied times x is being the slope and then the y-intercept. So that gets a little bit more difficult when you start thinking about the axis of symmetry for a parabola or something like that, trying to explain that conceptually. So what's your take on them memorizing those variables as, oh, it has to be negative b over 2a versus how it's supposed to be explained conceptually?
Yeah, so it's kind of